Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In the last class, we saw that how different schemes can be used to solve many different kind of flows. We looked at the exponential function, sine function and square wave, and we also looked at how different schemes behave when you want to use those schemes to discretize a linear convection equation. Okay. In today's class, what we are going to discuss is how to solve the nonlinear problems. Okay. So, as we have been discussing that most of the flows that we have in nature are nonlinear, and the Navier-Stokes equations which govern these flows are basically nonlinear, right. That is basically because of the convective term that we have in the Navier-Stokes equation. Not only in the flow, there are many different systems which are basically nonlinear. So, we need to find out how these schemes behave for nonlinear problem. Okay. We looked at some multi-step methods like Richtmeier and McCormack, two-step Lax-Van-Raaf, and we claimed that they behave a little bit better for the nonlinear problem. Okay. So, let us try solving a nonlinear problem today, and let us see how these schemes behave. Okay. And whether we are able to solve these problems, nonlinear problems using the multi-step schemes. Okay. So, before we go there, the problem that we want to solve today is called the shock tube problem. Okay. Many of you who are from aerospace background, they might be knowing what is a shock tube. So, basically it is a kind of tube, okay, and you basically generate shock in that. Okay. So, on one side you keep very high pressure, on the other side you keep low pressure, okay, and at t equal to 0, the diaphragm between the two sides breaks, and because of this very high pressure differential, shock starts moving on the right hand side, and consequently the expansion fan moves on the left hand side, and in between you have a contact discontinuity. It is a very interesting problem, and it is often used to check how the schemes are behaving, okay, because it is a highly nonlinear system. You know that shock is a kind of extreme nonlinearity. So, we need to see how these schemes behave for that particular problem. Okay. We will also look at some very simple problems when the regime is nonlinear. Okay. So, let us start the discussion today. Okay. So, the first thing that we need to note down, like if you have a linear system del u by del t plus c del u by del x, okay, equal to 0, and if you want to apply any scheme, let us say you are trying to apply this FTBH scheme, okay, then you can write it as a u I n plus 1 minus u I n by delta t plus c u, that is basically I, okay, this is FTBS. So, this is I n minus 1 n by delta x equal to 0. Okay. Let us say the c is positive. Okay. When it is a nonlinear problem, okay, del u by del t plus let us say u del u by del x. Okay. If you start writing in this way, okay, as we discussed in the last class also, that this is u I n plus 1 minus u I n by delta t, and let us leave it here for now. This is u I n minus u I minus 1 n by delta x equal to 0. Now, there is a u here also. Okay. So, we are trying to solve for u, and the u is also convecting at the speed which is u only. Okay. So, what is the value in the discretization? What is the value you should use here? Whether you should use u I, or maybe you should use u I minus 1, or maybe you should take an average of u I and u I minus 1. Okay. So, you have multiple choices, okay, and each choice can give you a slightly different result. Okay. So, this is called So, this is in the primitive variable, okay, or you can call it the non-conserved, okay, equation. So, what we can instead write, you can write it as del u by del t plus del u square by 2 del x equal to 0, okay. That would give you, you can write f is equal to u square by 2, okay. Then this is del u by del t plus del f by del x is equal to 0, okay. And then if you apply the FTBS in this, okay, now you do not have very hard choice, because you can easily fix this f to be the backward in step. This is what depends on x and this in time, okay. So, this is in forward. So, u y n plus 1 minus u y n by delta t plus f I n minus f phi minus 1 n by delta x equal to 0, right. So, here there is no problem, okay, because you have now defined f as a function which gives you the u square by 2, right. So, all the schemes that we have discussed. So, earlier we are calculating lambda equal to c delta t by del x, okay, if you put everything on the right hand side, okay. In this case, okay, it will not be c delta t by del x, but because it is a nonlinear problem, the u is changing every time. So, ideally it is like, let us say lambda equal to some propagation speed delta t by del x, okay. So, if it is a fluid flow problem, then it is like u plus c, okay, where u is the flow velocity and c is the speed of sound by delta t by del x, okay. If you look at the Euler equation, for example, in one dimensional flow, okay, you will have 3 characteristic waves, okay. One travels at the speed of u minus c, other at u, and third is u plus c, okay. Since your target is to get it the delta t, which is the minimum delta t which is satisfied everywhere. So, you can use this lambda delta x and the value which is basically the maximum value. So, instead of using u minus c or u plus u, you would rather use u plus c, okay. And even better, because u can be negative. So, you take the mod u, okay, or you can take the square root of u square plus v square, basically the u absolute plus c. So, this is how you get the delta t, okay. So, as you can see, because the velocity is changing every time. So, delta t will change every time, okay. So, this kind of simulation is called, basically you can call it local time stepping, okay, where you can calculate delta t every time using that relation which is lambda delta x by u plus c, okay. And you can fix the lambda, let us say you fix the lambda equal to 0.5, lambda is your CFL number, okay. Get the delta t every time, which will change every time, because your u is changing every time, c is changing every time. C is the speed of sound, which is nothing but square root of gamma r t or square root of gamma p by rho for an ideal flow, okay, ideal gas flow, okay. So, sometime let us to give an example, your time step will be delta t, the other time could be delta t plus delta t prime or delta t minus prime, and so on and so forth. It will change in every time step, right. So, if you fix the CFL number, your delta t changing, and in this kind of case the snapshot or basically the results that you are getting at different times, right. So, in these cases it is very difficult to find out the frequency. Why? If you want to find out the frequency, your time steps should be at equal interval, right. So, let us say if it is delta t, then basically you can find the frequency which is 1 by delta t, okay, or it will be rather 2 by delta t because of Nyquist criteria, okay. So, because it maps on both the sides, okay. So, in this local time stepping, you basically it is very difficult to find the frequency, because delta t is changing every time. So, if you have a signal, let us say you are analyzing the flow which is lid driven cavity, put a probe here, getting some data, let us say the pressure data, okay, or any data, velocity data, and this is your plot of time versus pressure, Okay. So, because that every point is at different delta t, you cannot do FFT or basically the frequency analysis because your delta t is not constant. The other way to do it as it requires some kind of CFD experience, okay, but that is very useful, okay, where you basically choose a delta t which is basically lower than all this delta t minimum across all time step. Okay. So, if you can somehow estimate that, okay, what is the delta t that can go the minimum delta t that can go during the entire simulation, and put a value which is even lower than that, right. So, what you have done, you instead of fixing the CFL, you actually fix the delta t. Okay. So, you have fixed the delta t, and in that case if you have the same signal which is let us say p versus time, okay, and it is actually at equal interval, okay, of delta t. So, let us say here, 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 okay, and then you can do FFT or many different kind of analysis. For example, you can do DMD, which is the dynamic mode decomposition, or SPOD, which is spectral orthogonal decomposition. Okay. So, the criteria for that is basically the time step at which you are simulating is constant, or at least when you are sampling, right. So, your delta t may be varying, but let us say you fix that I am sampling my data, basically writing your data at a fixed time step, which is let us say n delta t. Okay. So, this should be constant, okay, in order to do the analysis like this. Okay. So, this is called the sampling frequency. Okay. So, let us see the application of all these things. Okay, and this is just an example of the Richtmeier basically a discretization Richtmeier scheme. So, where we have replaced the C delta t with Cu with F. Okay. Now, let us go to the problem that we are trying to solve. Okay. So, this is the shock tube problem that I just described. Okay. So, in the left hand side, so I will call this left and this is right, okay, and in between you have this diaphragm. Okay. Use the red color. Okay. So, this is my diaphragm, okay, and this is the initial condition. You put the pressure very high on the left hand side and low on the right hand side, and because of very high pressure differential. Okay. So, what will happen that at t equal to 0, okay, the diaphragm will burst. So, as the diaphragm bursts, okay, so those who have taken any course in compressible flow or gas dynamics, you would know that when we create a very high pressure differential at a given location, okay, so the shock will form and this shock will start moving on the right hand side, okay, and because of that you will have the expansion fan which will move on the left hand side, okay, and so across the shock basically the pressure will increase. So, the pressure will increase like this, and here this will decrease, this will decrease like this, okay, and you will have the shock contact discontinuity. So, you will not see the signals of the contact discontinuity in the pressure, but you can see it in density. Okay. So, it is kind of a slip line. Okay. So, without going into the detail, let us get back to the CFD perspective, okay, that we want to simulate a high discontinuity. Okay. That is what the shock means in the CFD course. Okay. When you go to gas dynamics, you can look at some other features, some other thermodynamical features, what happens to the pressure, temperature and energy, entropy and so on and so forth. Okay. But here from the numerical perspective, we have given a very high jump, and this kind of flow is also called the Riemann flow, okay, Riemann condition. So, basically if you want to represent it, a condition is like this. Okay. This is very high pressure and this is very low pressure, this is PL and this is PR, and this is my 0 line. Okay. So, because of that the shock is forming. So, how to use a discretization scheme that can basically you resolve the shock. This problem is very hard. The reason for that is if you want to use any discretization scheme, right. So, here let us say your let us say this is my cell here, and I have the value, this is P small l and here is P capital R. Okay. So, what is the value that should be at the interface, right, because it is not a discontinuity which is basically continuous, it is a very sharp discontinuity. Okay. So, it is very difficult to estimate the value, and most of the schemes let us say if you try to use any central fencing, that will immediately fail, because you will start developing wiggles here. Okay. So, you have to have some kind of dissipation, okay, which can basically smear out the shock. So, the shock may be happening in very small region, but what your numerical scheme will do, they would basically smear this out, okay, and then your shock is basically happening in this thick region, let us say between this line, okay, and then it can try to predict the shock like this. Okay. Now, the catch is, if you smear it out too much, let us say you have a shock like this and smeared out too much, which we will see, let us say in the Lax Frederick scheme, which has got very high dissipation. So, your shock will look like this. Okay. So, that is not what we want, right. It is completely basically dissipated the shock, and you are getting something very different. Okay. It looks like a continuous shock. Okay. What we rather want to see is something like let us say even if there is a discontinuity, this discontinuity is very low, and probably it should be able to predict like this. Okay. So, we want a scheme which predicts like the blue line, even it can, if it can go better than this, that is better, and not the red line. Okay. The red line is not a good prediction. This red line, although it is more stable, okay, because of the added dissipation, it will give you the result, but it may be very smeared out. Okay. So, this is the condition. So, this is one particular condition, this is proposed by a scientist called Gary Sword. Okay. So, that is why it is called the Sword shock tube. Okay. And you can see that the jump here in pressure and the density initially. So, we will be solving it in 1D flow. Okay. You can also solve in 2D or 3D. So, for us it is a, just say this is a line, okay, and in between we have this is left of that center, let us say this is 0 and this is minus 0.5 and this is plus 0.5, right. So, this is a shock tube of length 1, okay, left hand side and this is right hand side, okay, and you have the conditions prescribed on the left hand side and the conditions prescribed on the right hand side, okay. And we want to see how the condition, from given the initial condition, how the flow is happening, okay, and at a given time, okay. And the left condition, let us say this is PL and this is PR. So, the PL by PR is basically 10, okay. So, if you are putting 1 on the left hand side, right hand side will be 0.1. You can also do it in a dimensional way, but the main thing to see here is the ratio between the left hand side and right hand side will be equal to 1 in the short shock tube problem. Similarly, you have a density jump also, rho L by rho R is equal to 8. Okay. So, the density jump is equal to 8. So, here you can see that rho L, rho R. So, we can use non-dimensional numbers. Okay. So, rho L is 1, rho R is 0.125, PL is 1 and PR equal to 0.1. See, all that matters in this particular case is the ratio between these two numbers. Okay. And we will be solving the Euler problem. Okay. So, that means there is no viscosity. Okay. Why we want to solve the Euler problem is because for this particular problem, okay, we have the exact analytical solutions available. Okay. So, you can use the method of characteristic, basically calculate the shock velocity at which shock is traveling, and you can find out the position of the shock using that shock velocity, because you know the Mach number on the left, Mach number on the right, okay, and so on and so forth. So, Mach number can be defined as gamma p by rho, square root of gamma p by rho. So, this is the speed of sound, okay, and as it is happening. So, this is let us say on the left hand side and on the right hand side, okay, and initially the velocity is 0 on both the sides, but as the shock will travel, velocity will develop, okay, and you can find out the shock speed, and at a given time you can multiply the shock speed with that, find out the shock time, and you will get the position of the shock, and accordingly you can get the position of the expansion force also. So, there are numerous literature available which basically talks about how to get this analytical solution, and I will not go into detail because that is not the subject. Here for our purpose we have some analytical solution available, and we want to compare our results, CFD results with that analytical solution. Okay. So, what are the governing equations we have? So, this is the Navier-Stokes equation, this is a 1D flow as I told you. Okay. So, governing equation, so you will have 3 variables, okay, rho, u and p, okay, there is just one velocity. So, one continuity equation, one momentum equation, and then one energy equation. Okay. And we will be writing in the conjugate variable form. Okay. So, you can see that as we have been discussing that conjugate variable forms are better for this CFD, okay, especially in the compressible flows, okay, where you have the dependence on density. The density is also changing with time. Okay. Now, you can see that earlier when we are trying to solve, let us say even in nonlinear case, we had this del u by del t plus del f by del x equal to 0. So, f was just like one scalar, okay, or u was just one scalar. Okay. Here in this case, we have this del q by del t and del f by del x. Okay. So, we have q is basically a 3D vector, okay, where it is rho, rho u and rho e. So, basically we have to solve for all three at the same time. Okay. All three will be updated at the same time. So, this kind of solver is called the coupled solver, okay, where basically we are updating all three variables at the same time. You can also do it sequentially. Okay. So, basically solve for the density first, then solve for momentum and then solve for energy. So, that is usually done in incompressible flows. Okay. In the compressible flow, because it is a tightly coupled system, so it is preferred to use all of them together. So, now you can have the q, which is a vector, okay, and this can be the vector. It has got 3 elements, okay, rho, rho u, rho e, and this is across, let us say you have I equal to this is your grid, okay, and then I goes from, let us say 1 to n x. So, this will be 3 to n x, okay, this is your array size. Okay. So, 3 is because of these 3 conjugate variables. This is the flux, okay. This is the mass flux, momentum flux and the energy flux. Okay. This is the inviscid one, and then if you are doing viscous flow also, then you have to consider the flux due to the viscosity also, which are given here. So, in this for today we will not be doing this viscous flux, but we will be only interested in the Euler solution, because we have the values available. Okay. In fact, if you use a viscous solution, it will add some viscosity, add some dissipation in the system, and your scheme will become more stable. Okay. If you use the stable term also. Okay. So, these are the Euler equations. Now, I have removed the viscous term. So, now I have just df by dx. So, both q and f are basically 3 cross nx and 3 cross nx. Okay. This is the size of the array. Okay. Or I mean depends on how you are writing. You can also have q1, q2, q3 separately, and see f1, f2, f3, f3 separately, which is basically all will be of size of nx. Okay. This one is rho hu, or basically rho e plus pu. Okay. So, here basically you can write it in terms of E will have both the internal energy as well as kinetic energy. So, you can write it in terms of the Cp will be RT by gamma minus 1, okay, and that will become, if you do rho E, so rho RT by gamma minus 1, that is P by gamma minus 1 plus half rho E square. So, this is your rho E term. Okay. So, rho E plus U will go here. Okay. So, as you can see, when as you go to the energy equation, the system becomes more and more complex when you want to solve it. Okay, but it is not very difficult. I will just show you an example. Okay, so, you can define an array of primitive variable. So, I have chosen rho, u and p. You can also, I mean it is your choice, you can use rho, u and t also if you want, right, because p equal to rho r t, right, or I mean you can use rho, u and s, where s is the entropy. You have to accordingly derive the equation, okay, or you can have rho, u and e, where is the internal energy. So, many different choices are possible. Okay. So, if you have the primitive variable, you can basically convert it to the conjugate variable, right. So, if I do not conjugate with q, so the q is a vector here. So, this is q1, q2, q3, that is rho, rho u, rho e, and you can use the primitive variable to calculate the conjugate variable. So, this is u1, rho is rho. So, this is u1, rho u, this is u1, u2 and rho e, and if I use gamma equal to 1.4, okay. So, you can basically derive, let me just see if I can do that. So, rho e, okay, and so that will become rho r t by gamma minus 1, right, and plus half rho u square. This is p by gamma minus 1 plus half rho u square. Okay. P is nothing but my u3, by gamma minus 1 plus half rho is basically u1 and u2 square, right, and gamma is equal to 1.4. So, you can write rho E is equal to 1.4 minus 1 is 0.4. So, 0.4 1 divided by 0.4 is 2.5, this is 2.5 u3 plus 0.5 u1 u2 square. Okay. You can also write a general code where you do not have to basically hard code this number, you can simulate for the varying gamma. Okay. Let us say instead of air you want to simulate let us say ozone, okay, or some other system where the gamma is different. Okay. Let us say the helium. Okay. In that case the gamma will change because that is a monatomic gas. So, in that case you can basically simulate it. So, you can have a general form that will be 1 by gamma minus 1 here. Okay. And similarly, from conserved you can calculate primitive, it is the same thing, just go back. Now, you have rho u p, okay, and you want to get it from the conserved, because you will be simulating always in terms of conserved variable. Remember our equation that will be solving is del q by del t plus del f by del x equal to 0. Okay. So, you will be updating always q, and if you want to get your primitive variable you can use it get from q, that is rho u and p. And then finally, the flux. So, flux you can calculate directly from your primitive variable. So, what you can do, you can convert from conserved to primitive, and from primitive you can calculate a flux, or you can write it completely in terms of the conserved variable also, because our simulation is anyway happening in q and f. So, why not calculate f directly from q. Okay. So, this is rho u is basically q2 rho u plus p, and if you take gamma equal to 1.4, you can write this equation like this in terms of purely the conserved variable, and similarly rho e plus p can be written like this, okay, multiply by u. Go back and work this, and you will see that you can write this fluxes in terms of the conserved variables directly. Okay. Now, this I already spoke that if you use basically you can calculate the delta t based on the CFL number and also what is the velocity that you are using. So, the net velocity, because you have 3 u plus c 3 eigenvalues u and u minus c, okay, and you want to get the velocity which is maximum. So, you can use u plus c. So, you can take absolute u plus c, or in 2D you can have u square plus square root of u square plus b square plus c, okay, and take the maximum value of that, because we want to find out what is the minimum delta t in the entire domain, right. So, your u may be different, let us say this is your domain, your u may be low here and u may be high here. Okay. So, we want to see what is the minimum delta t and use the delta t to simulate in one go. Okay. Then again in the next session calculate the delta t in the entire domain and use that. Okay. So, this is how you get the time step. So, I am just showing some picture, but I will also show you the code in the next class. Okay. So, here you can see I have used 3 schemes. This is the Lax-Frederick scheme, okay, this is McCormack scheme, and this is Richtmyer scheme, and this is the velocity. And you can see that there is some behavior here. First of all, this McCormack has like very abrupt jump, okay, near this discontinuity. Okay. Here also you can see there is some abrupt jump here in the Richtmyer, which the Lax and McCormack are not showing, but Lax has got some dissipation. I will zoom it and show it to you. And also you are not able to probably see here. So, there is an analytical solution as well, there is a black one is an analytical solution. So, if you go here for example, so this is the region where the expansion is happening, right. So, this is my expansion region. So, by the way this is the solution at some given time, I think here the time is equal to 0.1, okay, and this is the region where the shock is there. Okay. So, because the shock is moving the right side, so the pressure jump is happening on the left hand side. This is a pressure jump. Okay. Here is the pressure decay because of the expansion, and you cannot see the slip line here or the contact discontinuity here, but if you go to the analytical solution for density or even all those solutions. Okay. So, this is my expansion, this is my shock, okay, and this is my contact discontinuity or contact line, okay, contact surface, and this entire thing is the expansion fan, okay, because it is a continuous phenomena. Okay. So, this is an isentropic phenomena, entropy is not getting lost, this is isentropic expansion, but this is non isentropic. Okay. It is not an isentropic case, okay. It is adiabatic, but not isentropic. Okay. So, in the next class I I will take you through the code, basically how to write the code to solve this problem, and step by step, and I will show you the solution that we are getting. Okay. So, we will meet in the next class. Hope to see you there. Thank you very much.